Hello, Chemistry Clan. In today's lecture, we are looking at fractional precipitation. And fractional precipitation is basically, the ability to precipitate out one ion as a solid selectively over another ion that can precipitate. So long as their respective molar solubilities, and this is obviously tied to KSP, but so long as their respective molar solubilities are significantly different, one will precipitate out while the other remains in solution. A lot of environmental testing is done in this way, where you're looking at, environmental testing of, let's say, harmful metals in your drinking water. As an example of where we could actually utilize this type of property. We have a water sample. We want to know what types of heavy metals or other metals are in there, and we can do selective precipitation of these metal ions. We can then get masses of them and then get us a percentage within the sample as far as how much of lead is in your drinking water or something of that type of nature. So the two ideas that kind of run along this fractional precipitation concept are that, the molar solubility of, let's say, one ionic solid that's in the mixture is going to be much less than the molar solubility of a second solid that could possibly precipitate. The fact that we have such a big difference in those molar solubilities is why the solid that has the smallest value in its molar solubility, or is the least molar soluble, will be the ionic solid that's going to precipitate first. So that's kind of the first thing when we're looking at fractional precipitation ideas. We have to compare molar solubilities so that we can figure out what is going to precipitate out first, and then what is sequential in that aspect. The second piece to this is almost kind of a question, meaning almost like an error type question, because these are all equilibrium processes. So by our rules of equilibrium, that means that, these players within K can't go to zero. So even though we're talking about a precipitation process or a fractional precipitation process, that first ionic solid that we're saying here would precipitate first, there would still actually be some of the ions left in solution. Again, because this is an equilibrium-driven process, this is a KEQ, or more specifically KSP process. So there must be some quantity of the ions in solution. More than likely, it's going to be a really, really, really small quantity, but a quantity nonetheless. So another player to this is how much of that ionic solid that precipitates first and we could call that, our ionic solid 1. How much of that precipitates first? How much of it is still left in solution? That's generally a follow-up that we see with these types of questions, with fractional precipitation. One is I think the easier angle which precipitates first, and that's a molar solubility question, a comparison of molar solubilities. And then the second is basically, how much is still left in solution? Remember, this can go back to environmental testing, and one could argue that this is like a percent error idea, meaning that this is what we quantitated as far as how much, lead is in your water, but realize that we can't, that there is a margin of error. And so how much of this ion would actually still be in solution that we just could not quantitate from the precipitated solid material that we got from the process. So those are the two aspects with fractional precipitation, types of questions. So let's look at an example. So our question starts with, we have a solution that is found to contain 0.01 molar potassium iodide and 0.1 molar sodium chloride. What we're going to do to this solution is slowly add solid silver nitrate to the solution. So our first bit of this is assuming that there's no change in volume. Since we are adding a solid, right, we're adding the solid silver nitrate, what is going to precipitate out first? Since we're adding silver to the solution and we have halides in the solution, namely iodide and chloride, Now we could have two possible products that would precipitate. One would be silver chloride, and it has a KSP of 1.2 times 10 to the negative 10th. The other one would be silver iodide, and it has a KSP of 1.5 times 10 to the negative 14th. So that's part A, if you will. And then part B is what is the percent of the ion, then this would be chloride or iodide, is still in solution when the more soluble ion begins to precipitate. And so that's our second question. So just to go back, we have a solution, right? We have a solution that is containing two things. We have 0.01 molar potassium iodide. We also have 0.1 molar sodium chloride. Really what we're interested in is the iodide and the chloride. That's really what we're going for here. We then add solid silver nitrate to that, and now we are going to start a precipitation process to occur. What precipitates out first, the silver chloride or the silver iodide? And we have information as far as their KSPs. We actually might already be able to predict the idea that silver iodide probably falls out of solution first, given how small its KSP is relative to the silver chloride. But to be honest, we still want to go through this ritual of solving for the molar solubilities to be absolutely positive. So that's really our part A question. Part B, which we'll rephrase again once we get to it, is basically saying that once we figure out what precipitates out first, right now we're thinking, the iodide is going to precipitate out first, the silver iodide. How much of that ion is left when the other one begins to precipitate, right? So remember, we're doing maybe some environmental testing here, and we're trying to get rid of this one ion from solution so we can quantitate its percentage within the actual drinking water or water system. But there's an error that goes along with that, meaning that there's always going to be a little bit of that ion still left in solution, since it's a equilibrium process or an equilibrium driven process. So even though we've quantitated how much of that ion is pretty much there is still some that's in solution. So what is the quantity of that left in solution? So that's really part B. So we'll rephrase that again when we get to it. So let's look at part A. So really what this is basically a common ion. Basically times 2. We need to figure out and compare the molar solubility of silver chloride versus the molar solubility of silver iodide. So that means for each one of these, we need to have an equilibrium reaction, and we need to have a KSP for the actual process. So I'll do this for each one, individually. So for the silver chloride, we would have something that looks like this. And our KSP would be equal to the silver plus 1 times the chloride minus 1. That now allows us to put together our ice table. Initially, we do not have any of the silver. We're adding that slowly throughout this fractional precipitation process, but we already have a concentration of our chloride, which is 0.1 molar. And so we end up with these equilibrium values with regards to the molar solubility. Remember that this is, kind of like X, right? As far as this is like plus X in both regards. So now that we have that, we can substitute into KSP and solve for S, right, for our molar solubility. So our KSP, which was 1.2 times 10 to the negative 10th for the silver chloride, is equal to S times 0.1 plus S. We can again assume change is small, relative to the value of our equilibrium constant. And so our value is equal to S, as far as our KSP value, is equal to S times 0.1, or our solubility for the silver chloride is equal to 1.2 times 10 to the negative 9th. So that's our first molar solubility. We figured that out for the silver chloride. Now we have to do all the same number of steps for now the silver iodide. So again, we have our next equilibrium reaction that we have to do. Again, this is specific for the silver iodide, while our other one was specific to the silver chloride. So the reaction here is looking at silver iodide and how it dissociates into water to produce silver plus 1 and iodide minus 1. And that gives us a KSP that's actually equal to, right, our silver plus 1 times our iodide minus 1. So there's our KSP and equilibrium reactions. 2, we can go to our ice table then. And we have those two ions that we're looking at specifically, the silver plus 1 and the iodide minus 1. Initially, just like above, we don't have any of the silver plus 1. And we have 0.01 molar for the iodide. Right, that's coming from our potassium iodide, just like our earlier example for the chloride is coming from the sodium chloride. There's a change, which would be plus S for both. Or if we want to say, that's like plus X for both. And then we have an equilibrium concentration with regards to S of S for silver and 0.01 plus S for the actual iodide. Once we have the ice table filled out, we can now substitute back into KSP and solve for our molar solubility. In this case, specifically the silver iodide molar solubility. So our KSP is equal to the silver plus 1 times the iodide minus 1. KSP for silver iodide was 1.5 times 10 to the negative 14th. And that is equal to S times 0.01 plus S. Again, we can make our assumption motif works here. So we can assume change is small relative to initial concentration. We are starting with the solid, silver iodide in a way, and so we are starting with initial starting material. We do have a very small KSP, and that allows us to make this assumption. So our 1.5 times 10 to the negative 14th is equal to S times 0.01. So that's now our simplified equation, and so we can solve for the molar solubility of our silver iodide to be, our 1.5 times 10 to the negative 14th divided by 0.01, or we have a concentration of 1.25 times 10 to the negative 5th molar for the actual silver iodide. So if we look at the different solubilities, we have a solubility of silver chloride to be 1.2 times 10 to the negative 9th molar, and we have a solubility of the silver iodide above here to be I have a mistake above, so we'll correct that. It should be 1.5 times 10 to the negative 12th molar above. So those are our 2 molar solubilities, and the fact that the one is so much greater means that the silver iodide will precipitate first. As we go and we continue to add more and more silver to the solution, we will reach this threshold of solubility for the silver iodide much faster than we will reach that threshold for the silver chloride. The silver chloride is way more soluble, and so we'd have to add much more silver in order for that particular solid to now start to precipitate out of solution. So that's how we can figure out what will precipitate out first. We really just have 2 questions both asking, okay, what is the molar solubility? And within each of those questions, it's really a common ion question. So we have to use a common ion procedure for the silver chloride, and then use a common ion procedure for the silver iodide. And then comparing those two solubilities like we've just done here, then allows us to predict what is going to precipitate out first. So in this case, it would be the silver iodide that would precipitate out first. So that's part A. Part B. Part B, now we actually know some more information. The question was read, how much of the ion that precipitates first will be left in solution when the other ion begins to precipitate. So that's the question that we had above, and now that we know what precipitates out first, we can maybe reword it a little bit. It's really asking, how much iodide, right? Because that's what precipitates first. How much of that will be left in solution when the chloride begins to precipitate? So that's really the question, right? A little bit more specific now that we know what ion is precipitating out first. So from that standpoint, we really just want to do the same process as far as what is the equilibrium reaction. We've actually already written that. And what is KSP equal to as well. These are things that we've both done already, but let's just do it again. We're specifically talking about the iodide or the silver iodide. And so there is our KSP, or there's our reaction, our equilibrium reaction, which allows us to generate the KSP equation. And remember that was equal to 1.5 times 10 to the negative 14th as far as the KSP value. So there's our KSP process. We now want to go to our ice table to now realize or figure out what we can plug into that KSP expression. And so the difference here is, we're really not looking at an ice table per se. It's really a question of equilibrium. So while we're used to this idea of using the ice table, really this is not necessary. Just want to figure out how much iodide is there based off of the silver chloride molar solubility. All right, this is definitely a tough one for students to get past. Right? There's really no need for the ice table here. Really all it's asking is that given our KSP for silver iodide of 1.5 times 10 to the negative 14th, given our silver concentration is based off of the silver chloride, because that's what precipitates out second, we can now figure out how much iodide would actually be left over if we were at that concentration. So that means we really can just actually jump to, substitute these values into KSP and solve for iodide. And that would be iodide at equilibrium. So, the KSP, we're very specific. We're still looking at this silver iodide. But what we want to do now is change up what we're plugging into it. So our KSP is 1.5 times 10 to the negative 14th. That hasn't changed. But here is what has changed. Notice that now I have a silver concentration of 1.2 times 10 to the negative 9th molar. Remember that the molar solubility of silver chloride is equal to 1.2 times 10 to the negative 9th molar. So our silver plus 1 concentration also has to equal that to cause the chloride, right, the other more soluble ion, to precipitate first. And that's what the question is asking. How much of the iodide, the ion that precipitates first, the iodide, how much is left in solution when the other ion being chloride, precipitates? So we're plugging in the silver concentration that's going to cause the chloride, the other ion, to precipitate. And if we're at that level of silver to cause silver chloride to start precipitating out, then that level must be 1.2 times 10 to the negative 9th molar. How much of that iodide is still left in solution? Remember, this is that percent error kind of idea, that even though we've already, can quantitate how much of that iodide is precipitated out by filtering it, isolating it, weighing it, etc., etc., there's always going to be a little bit of that iodide left in solution. So how much is actually there? So that is why we plug in that 1.2 times 10 to the negative 9th for the silver concentration. And so we can solve for our iodide to be equal to then the 1.5 times 10 to the negative 14th, the KSP, divided by 1.2 times 10 to the negative 9th, that silver concentration. And we end up with a concentration of that iodide to be 1.25 times 10 to the negative 5th molar. And so this would be iodide that's still left in solution. I mean, the silver iodide has been precipitating out. We keep adding more and more of the silver, and so we have more and more of the silver iodide precipitating out. But then all of a sudden we reach this upper threshold that's now going to cause the silver chloride to precipitate out. And so how much of that iodide is still there? we find that there is still a quantity, even though it's very, very small. So to figure out the percent, right, the percent of the iodide left would then be equal to, how much is there, divided how much we originally began with, times 100, and we find 0.125% of the iodide is still in solution. So while it is, a selective precipitation or a fractional precipitation, we still don't have the ability to remove everything from the solution. So there is still some material that's actually left in solution. And here we've quantitated that to be 0.125% of that iodide is still there. And so you could classify that as almost a percent error idea. But that's generally how these fractional precipitation questions work. Part A is what precipitates out first, and that's really just two different equilibrium processes, common ion processes, solving for individual molar solubilities. And then usually the harder one for the student class is this piece, is part B, where you're trying to figure out, how much of that ion that precipitates out first is left in solution once the more soluble ion begins to precipitate. So make sure you get some practice on these aspects. That is it for aqueous ionic equilibria. We are now moving into a brand new topic. Maybe I shouldn't say brand new, but we're headed back to thermodynamics. We covered thermodynamics in part 1 of general chemistry, looking at enthalpy and delta H. Now we're finishing that conversation with thermodynamics part 2. And so that's what the next lectures will discuss.